Let's start. Hello, we are Team 9 here to present our interim presentation for advanced design for manufacturability on analysis and redesign of a raclette fondue set. The team members are Jacob, Marisa, Sajad, Karina, and me. So our product is used for grilling, food, cooked fondue, and raclette. It requires heating of various foods for dipping. The set consists of temperature controlled cooking pot with electric or gas heating element. It also includes heating pans to store food. The minimum number of sets we aim to manufacture per year is 5 million. So it brings down our cost per set to $60. Uh, on the left, the chart shows the current market share of the product, and on the right shows the customer we want to cater to. So our primary customers would be household consumers such as families, peer groups, uh, which serves families of 4 to 6 people and keeps food warm over the course of one meal. And our secondary customer would be food catering businesses and hotels. We aim to serve larger customer base and demographics.
Our exploded assembly diagram, which helps us to determine the best ways to assemble the product. As you can see, each of the items is listed and has the quantity attached to it. We also did a functional analysis or FAST diagram to determine the most important functions for our system. As you go towards the right of the FAST diagram, you explain the how you accomplish the functions, and as you go towards left, you explain why you are trying to accomplish the functions. Some of our most important functions include adding heat, containing the fluids, containing the solids, controlling the temperature by changing heat and stopping heat, serving food, and doing things like assuring dependability by preventing burns.
The first assembly sequence is of the bottom-up type and is more realistic. It begins with the base, followed by the dial assembly fondue and the dial assembly grill. Then it has the plates, and sandwiched between them are the grill coil, holder, and fondue bottom. Assembled vertically on top of them are the burner cover, fondue coil, spacer, and the top cover. The arm and side brackets are placed next, followed by the grill plate. The pan and pot assemblies are the final assemblies to be added. The next sequence is the top-down approach. This sequence is the reverse of the bottom-up assembly and begins with the arm instead. It does not allow for easy attachment of the coil and is hence less realistic. So here we have the assembly sequence analysis, which compares the sequences, scoring them in categories from 1, that is the worst, to 3, which is the best. The sequence from bottom up was the better of the two, especially for ease of locating the parts. As can be seen in the function component mapping matrix, heat is added to the top cover, fondue coil, burner cover, fondue bottom, and grill coil to heat the food as well as the fluid, while the pot and pan assemblies are used to contain them to serve food. The arm and the plate serve to prevent burns, while the side bracket and cord show convenience. The dial assembly fondue and dial assembly grill can change and stop the heat for the purpose of temperature control.
This is our bill of materials. It includes each part of our assembly, along with their respective quantities and current material. We also determine the manufacturing and assembly processes for each part. Finally, we were able to provide rough estimates for the total unit cost by doing various analyses we learned in class, which allowed us to determine the material cost, processing cost, assembly cost, and tooling cost per part for each part in our assembly. As you can see, some of the purchase parts that we have high material costs, as these estimates are for individual units and not bulk orders. So this kind of led to our overall production costs being higher than we expected, but maybe a more refined search can provide us with a more accurate bulk production cost.
Our product family design details a variation of the pot assembly intended for the secondary customer group that we identified, food service such as caterers for larger events. These users need to serve a larger volume of people than a regular household, so a larger pot volume would be beneficial to increase the amount of fondue or liquid that can be heated at once and increase the amount of time between restocking so they can serve more people. The functional differentiation table for the customer groups is shown here, referencing the different functions of the product identified in our functional analysis mapping. The product still needs to perform every function for both customer groups, but the difference between the product variation comes from how much fluid the product needs to contain at a time. Here's the component commonality table for the product family. We classified the pot assembly as the only module that is unique for each product variation because in our function component matrix mapping, we identified the pot assembly as the only component fulfilling the contains fluid function. Depicted here are isolated pictures of the original pot assembly on the left and a larger pot assembly on the right. You can see the step in the larger pot shape at the bottom to allow it to fit in the same space as the original pot assembly while allowing the pot to be taller and wider, increasing the pot's volume. And here are two section views depicting the common interfaces between the original and larger pot assemblies. The pot just sits in place, so to have the same interface as the original pot, the larger pot just needs to have the same shape at the bottom as the original. Finally, here is our product differentiation assembly sequence for the product family, following assembly sequence number 1, which we identified to be the better of the two sequences analyzed. The pot assembly is already installed at the end of the sequence, which is already optimal for the delay differentiation method. That wraps up our presentation. Thank you.